All right. We come now to chapter 4. This is the most important part of this book. Everything else that follows is going to be based to a significant extent on what Hume argues here. It's also the most important argument Hume ever came up with. It is, to my mind, the most disturbing skeptical argument possible. Not because of how much it places sort of in doubt, right? Nothing can beat the evil demon argument for placing something in doubt, right? It places everything in doubt, except as Descartes pointed out, that he existed. It's that, unlike the evil demon argument, which no one, Descartes included, ever really took seriously, like no one ever heard the evil demon argument and was then like, damn, well, now what do I do? I don't even know if I have hands. Everybody was like, well, this is an interesting puzzle. I wonder how we solve it. The problem of induction, which is what chapter 4 is going to be about primarily, is a kind of skepticism that you can find yourself genuinely, or at least I find myself genuinely worrying about. It's an incredible intellectual achievement to have come up with this argument, and it has, to a significant extent, set the stage for philosophy ever since. The problem of induction is right up there with some of Plato's work in terms of influence on philosophy going forward. As much as I'm impressed with Hume's work here, I'm actually not going to stick too closely with how he presents the problem. I think there's a clearer and better way to present the problem than the one he chooses. It's my hope that my way of presenting it won't lose any of the important content that's in there. So do read the chapter, but I'm going to explain it in a different way in case the chapter doesn't, the chapter's way of explaining it doesn't work for you. All right, what I'm going to do is I'm going to start with coin, regular quarter. And I'm going to flip this thing about 20 times. And I want you to also do that if you can. Some people can't flip a coin. I've done this in class before where like I send a coin around. I always make sure it's someone else's coin because it was my coin. I don't think I'd get it back. But I send it around the class and everybody flips and then we record what it is. And depending on how many people there are in the class, maybe we have to go twice or 3 times or something like that. You want a fairly robust set of results. You want minimum 20, maybe more. Now, I'm not going to have you watch me flip this thing 20 times. But I am going to do it, and then when we come back, you will see the results. And I want you to do it for yourself, write it on a piece of paper. If you don't have a coin to flip, just anything that has a 50-50 shot will work. Anything where you don't know how it'll turn out, but it can turn out one of 2 ways. So, come back in a bit for the results of my exciting coin flipping. All right, here are my results, rather sloppily written. T for tails, H for heads. Now, what I'm going to do with mine, and what I encourage you to do with yours, is to try to find patterns, right, in this set of data, right? So I've got 20 coin flips. I'll see if I can find some patterns. And I don't want you to find patterns or try to find a pattern that holds true of the entire set of data. Feel free to find patterns that only hold for a part of the data. So for example, for my 2 through 8, I got straight heads. It was actually a little weird while I was doing it. It's not an entirely likely result. So it's 1/2 by 1/2 by 1/2, so that's 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. Less than a 1% chance of getting them all in a row. But of course, keep in mind your chance of a further head wouldn't be really low; it would still be 1 and 2. Let's avoid the gambler's fallacy. If you don't know what the gambler's fallacy is, maybe that'll come up at some point in this discussion. But here is a very simple pattern. That held for me in rows 2 through 8. You always get heads. It's a very simple pattern. Every time you flip a coin, you get heads. Now imagine you were someone who had only started observing this coin flip sequence at 2. What would you have expected at 9? Well, if you know what a coin flip is, and you know that, I mean, it's not 100% random, but it's really, really hard to predict, and both sides are roughly equally likely to come up. It's probably not entirely the same, given that there's different tails for different coins, but whatever, put that aside. If you know what coin flipping is, and you're being reasonable about it, what you'd say at 9, like just before I flipped to do 9, what you would have said was, well, I don't know, right? It could be tails, or it could be head, or it could be tails. But let's say you didn't know the process. Let's say you didn't understand the process, and all you had to go on was this set of data, but you had only come in at 2. Would you expect 9 to be heads? Maybe you would. Right? If you didn't understand the process that produced the data, you might think that this pattern would continue. Right? Let's find another pattern. Here, we'll erase this yellow line. Are there any other patterns? There are. One pattern that jumps out at me is right here. Right? So we have going from 5 all the way through 17. Right? You have 4 heads, 2 tails, 4 heads, 2 tails, and then you have a head. Now the question is, if let's say you came in at 5, right, and that's all you'd observed, what would you expect at 18? Again, not knowing what process produced the data, or at least not understanding the process. Would you have expected another heads? Right? Maybe you would, right? Because you get 4 heads, 2 tails, 4 heads, 2 tails, and then a heads process started again. Here's another one, and this one's not quite as, let's say, detailed a pattern. But let's say you came in at 2 again, and you stayed through 20. So the only one you missed was 1. You might come to think, well, heads can come up in any sequence, right? You can have heads in a row any number of times. You can have a single head, you can have 4 heads, you can have any number of heads, but tails always come in pairs. You might think that by looking at that data if you didn't see that first singleton tail, right? Or even if you'd seen the singleton tail, but you didn't know that the one position was where it started, right? If you had this whole set of data, you might think, well, if there was data before, it might be that tails only came in pairs then too. It might be that before the one I observed first, it could have been that there was another tails. Here's the point. In fundamentally random or like statistically noisy processes, you can find patterns, right? We're really good at finding patterns. Our brains are built for it. If you've ever had someone try to point out constellations to you, or if you've ever tried to find constellations yourself, or if you've ever found shapes in clouds, you realize that we can find patterns in things that just they're not there. We can find images where there aren't. We can find patterns in data that don't exist. Right? If you ever watch SportsCenter, I don't know if anyone still does that, but if you ever watch SportsCenter, they will find the stupidest patterns in sporting results, right? The Bulls have never lost a back-to-back that started on a Tuesday during a winter month, right? Things like that, right? Although, given recent Bulls history, that's almost certainly false. Unfortunately, I'm a Bulls fan, by the way. It went really well in the 90s. Not so much since. So here's the point I want to make with the coin flipping. Hopefully you flipped your own coins and you found that you could also detect similar patterns. And remember the way I set this up, right? The situation is you haven't seen all the data, or alternately, you think you might not have seen all the data. You don't know the nature of the process producing the data, and the data will continue, right? And you have to form expectations about what the next data point will be. In this case, heads or tails. The reason why I point those factors out is that that's the situation we're in with basically any scientific issue. That's the situation we're in anytime we use induction. Why? Think about what induction involves. So here I'll give you an example of an inductive argument, a really bad inductive argument. In fact, one of the most common examples of a bad inductive argument, right? And I'll actually represent it the same way, right? As I did this. So we'll do one, only I won't do 20 data points. I'll do 8, right? Let's say what's happening here is I'm observing swans. Right? If you already know where this is going, I was going to say keep it to yourself because usually when I teach this, I teach it in front of people. But how are you not going to keep it to yourself? This is a video. I mean, if you're watching these with anyone else in the room, keep it to yourself. Don't ruin the surprise for them, I guess. All right, let's say the first swan I observed was white. All right, second swan I observed was white. Third white, fourth white, fifth white, sixth, seventh, and eighth. Or in other words, I've observed 8 swans. They've all been white. All the swans I've seen are white. The way this would work in an inductive argument, this kind of induction is called enumerative induction, where you're just like numbering all the cases you've observed, is each one of these 8 instances of making an observation would be a premise. I'm not going to write it out because it would take forever. But the first premise would be the first swan I saw was white. The second premise would be the second swan I saw was white, and so on and so forth. Now, if you're doing an induction of the kind that Aristotle had in mind, the kind of conclusion you would draw from this argument would be, presumably, all swans are white. Now, the reason I use this example is, of course, not all swans are white. There are black swans. And the term black swan is the most commonly used term to describe failures in induction. Now, we already sort of pointed this out when we looked at Aristotle. Aristotle was aware that you didn't get to certainty with induction by itself. That's why he thought you needed that last step of intuition. But intuition is not going to work for Hume. Why? Well, Hume's an empiricist. What is it that intuition is getting you? Intuition is supposed to be some kind of direct connection between your understanding, according to Aristotle, and the general principle that you become aware of. But that's not how it works if you're Hume. If you're Hume, the only way you have to take in information is through impressions. And impressions come in one of 2 ways. They come through your sensory modalities, they come through your sense organs, or they are your passions, the things you feel inside. But you don't feel general principles, and you can't observe general principles. You can only observe particular things. So the problem of induction arises for Hume because Hume is a more thoroughgoing empiricist than Aristotle. I think it's probable, and this is a controversial thing I'm about to say, but I think it's probable, that Aristotle was aware there was a problem with induction. The reason he, in fact, this is the way I taught it to you, the reason he has intuition in there, the reason he has nous or understanding, is that he's like, well, there's a problem in the offing, and I'm just going to get rid of it. I'm going to say that we must have this extrasensory ability to directly tell which of the inductively arrived at principles are genuine principles, genuine laws. Right? But let's say you don't have that. Let's say all you got is the data. Well, it always seems like it's possible for any conclusion of an inductive argument to be wrong. And knowing that, statisticians have made it their business to try to figure out, given some set of data, how likely a principle like all swans are white is true. Right? So, and you have to take account of a lot of things. You have to take account of how many cases you've looked at. That's really important. Right? In other words, you have to look at sample size. You also have to look at how varied the circumstances in which you made the observations were. Right. So from what I understand, part of what was going on with the all swans are white example is that Northern Europeans who, I don't know if he was the first one to come up with this example of all swans are white, but he uses it. I'm not even sure if he uses it in this book, but he definitely uses it. Northern Europeans tended to see swans not in their natural habitat because I guess it's too cold in Scotland and like Denmark and stuff. So they would see like swans in menageries. Like rich guys would own swans in that one room of their house that was like warm enough for the swan to like be comfortable and not fly away. But they wouldn't have black swans Like if someone brought them a black swan that they paid for, they'd be like, I don't want that, kill it. Right? Just bring me white swans. So in that case, you're looking at a sample, even if it's a large sample, it's been biased systematically, right? The infrequent black swan is being culled, being removed from the sample. So you have to make sure things like that aren't going on. And you have to know something about the total number of cases, right? So for example, when polling happens, when you try to figure out what's the likelihood that candidate X is going to win given the responses to this polling question, you have to not only know how many people you've polled, you have to not only have some kind of randomization thing going on to make sure you're not only calling like old white dudes, in which case Trump, right? You also have to have some idea of like how large the voting population is. There's all sorts of stuff that goes on with this. The whole idea behind this, though, is to be able to say, all right, we know it's not certain that all swans are white, or we know our inductive conclusion isn't certain, but to apply some probability to it, right? Now, the probability that all swans are white given 8 observed white swans is pretty low. But you can imagine a better set of inductive evidence where someone can be like, well, there's 97% chance, right, that the inductive conclusion is true. I've seen people present the problem of induction as though all it was pointing out that inductions can lead to false conclusions. That's not the problem of induction, because that problem is relatively easily dealt with. Now, I will point out, the fact that induction can fail means that if you're one of these people who demands certainty for something to count as knowledge, if you don't think you know something unless you're 100% certain of it, then it's a pretty significant problem. Because it seems like induction can't ever get you to 100% certainty. But let's say you're being reasonable, or what I would consider reasonable, and you're like, nah, if you're 99% certain it's true, you know it, right? As long as it actually doesn't turn out to be false. If, however, you adopt this fallibilist position, then there's a bigger problem in the offing. Right? Because here's what's going on in every kind of induction. I'm going to draw a couple of circles. Oh, I dropped my pen. It's not even really a pen, it's a stylus. Right. Circle 1 and circle 2. This larger circle I've drawn here, I'm going to label E for everything. And this smaller circle, I'm going to label O for observed. Here's what happens anytime you do an induction. When you do an induction, you're taking some observed set of cases. The cases that appear in circle O. And you're taking a look at the data you've gotten from those observations, and you're trying to come up with principles that are true of everything inside the observed circle, right? So you've got a whole bunch of data points. These dots represent data points, right? And you're trying to come up with some principle, maybe some mathematical formula, hopefully something more sophisticated than all swans are white. But, like consider a scientist, consider Newton. Here, we'll use Newton as an example since Newton was dear to Hume's heart. If you're Newton, you're basing your laws of motion and you're basing your theory of astronomy, you're basing your laws of gravity, your law of gravity, on a set of observations. And that set of observations is basically just some observations made in the northern hemisphere of planet Earth from around the mid 1500s, or actually, no, the late 1400s to the early 1600s. That's it. You don't have any other reliable source of data. Isaac Newton was working from the observational results of a guy named Tycho Brahe, who was a Danish astronomer, making just incredibly detailed observations of the night sky without having a telescope available. If you're interested in scientific history at all, look up the way Tycho Brahe made his observations of planets and stars and stuff like that. Newton had that set of data. He had data from people who lived after Brahe, who continued making those same kinds of observations, but it only really started with Tycho Brahe. And the observations had only come from a really small part of the world. It came from Europe, basically. Europe for about 150 years. His observations when it came to motion were all made in Europe in a few private homes over the course of about 100 years, really starting with Galileo and going all the way through Newton. So that's his observational base. That's the data he has, right? And that's the data he was looking at to come up with the formula that he said described how everything in the universe moved and the gravitational relationship between every object in the universe and every other object in the universe. What happened was Newton took his observed set of cases and he came up with a set of principles. Those principles are the laws of motion, the law of gravity. And then he said, those principles, which are definitely true of the observed set of cases, right? Or rather, they hold true of the observed set of cases. What the principles say will happen is what actually happened in the observed cases. Those principles aren't just true of the observed cases. They're true of all the cases. They're true of everything. Every induction involves a projection of patterns found in the observed cases. And so you take those patterns you found in the observed cases and you project them out onto all the cases. You say that this pattern that's held true of all the cases we've observed will also hold true of all the other cases, including all the cases that are too far away for you to observe. So Newton was staking out a position about what the stars would look like if you were in South Africa. He knew about South Africa, I think. It now occurs to me, I don't know, I forget. No. The Portuguese went around South Africa in the 1500s, so Newton knew about South Africa. He would have been making predictions about that. What the stars would look like in the night sky, right? How they would move across the night sky, even in other parts of planet Earth. He was making predictions about what little round metal balls rolling down inclined planes. This kind of experiment that Galileo did. He was saying, like, these things will behave the same way no matter where you do the experiment, even though he only had the results from Galileo's setup in Italy and a few other people throughout Europe and his own setup in England. But it's more than that. He was making a claim about what every star is doing. Right? He was making claims about how every body in the universe behaved. Now, at the time Newton was writing, they thought the universe was quite a bit smaller than it turned out to be. Surprisingly enough, it's only in the 20th century that people became aware there was more than one galaxy out there, which is why if you look up what galaxy means, it basically means universe. You have to keep in mind how bold this claim is. If you were to draw to scale, right, the set of observed cases Newton was working with, compared to the set of cases his principles claim to be true about, you wouldn't be able to see the observed case circle, right? And even if it showed up as a dot, I wouldn't be able to contain on this screen the everything circle. And that's just taking into account the size of the universe. You have to also consider the fact that Newton was saying these principles have always been true. It's been true for the entire universe at every moment in the past, and it will be true of the entire universe for every moment in the future. Right? So this is fairly bold. Right? And the fact that the set of cases you haven't observed, but that you're nonetheless making the claim about is so large is part of why any set of inductively arrived at principles could turn out to be false. But you have to wonder, like, what's going on when we do this? Right? What allows us to make the claim that the principles that are true in our time and in our region of the universe are going to hold true of objects far away from our region of the universe and far distant from us in time? I'll make this a little more practical. The debate that once took place between two, there was this debate several years ago between two giants of American intellectual life, Bill Nye the Science Guy and Ken Ham, the dude from Answers in Genesis. And they were debating about whether evolution was true. All right, cool. And the kind of evidence Bill Nye brings up in that debate, which you can watch on YouTube, the kind of evidence he was bringing up was like, well, look at all these sediments, right? Like, let's go to the Grand Canyon and let's look at the different colors of the dirt and earth in the Grand Canyon. And let's take a look at how long it takes for that kind of sediment to build up. Or rather, in the case of the Grand Canyon, I guess, how long does it take for a river to cut through that much sediment? Or take a look at ice cores, right? We know how long, we can observe nowadays how long it takes for a layer of ice to form in Antarctica. So when we, take ice cores from Antarctica and we see, hundreds of thousands of layers of ice, we know that it takes hundreds of thousands of years to make that. That's Bill Nye's argument. Fundamentally, what's going on here is Bill Nye, in order to establish that the Earth is older than 6,000 years, which is what Ken Ham was saying, is he's saying, all right, let's observe how processes nowadays work. And let's project those same fundamental processes backwards in time. Whereas someone like Ken Ham would be prepared to say, no, once upon a time, ice formed in Antarctica quicker, right? In fact, way quicker. It used to be that there would be like 30 layers of ice put down a day in Antarctica. Now it's slowed down. Or tree rings. People like Ken Ham, people who are what are called young Earth creationists, have to believe one of two things. Either God created trees with a bunch of tree rings in them to trick us, which is, this doesn't seem like an altogether up and up thing for God to be doing. Or, in fact, it seems like the evil demon worry all over again. Or God set things up so once upon a time trees formed tree rings quicker because we've got trees that have tree rings that show that they're older than 6,000 years old. That we don't have many, but there are some. So this kind of argument that people will make to show that certain things are true about the past rely on the idea that the processes you observe in the present or in the recent past when we have data, those processes worked basically the same way in the past. Right? And when people make predictions about things like, well, in, several trillion years, or I guess billion years, in several billion years, the sun's going to explode and devour the earth, but not before then. Well, what they're doing is they're using data we've gotten from making stellar observations about, what stars look like before they blow up, before they go supernova. And we're using, it's actually a lot more complicated than that because we're also applying laws of physics that we've developed in other contexts to the case of stars and their life cycle. But that's basically what we're doing. We're predicting the future by saying the processes that hold true in the observed cases, basically now and in the recent past, will continue to hold true. So here's the question. What reason do we have to believe that? Given that we know that sometimes fundamentally random processes can appear as though there's a pattern and an order to them, but they only appear that way because we haven't seen all the data, because we come midway through, right? So remember with mine, someone who missed flips 1 through 4 and had been there from flip 5 through flip 17 would confidently predict an H. That would fit the pattern they observed. But they didn't get an H. Right? The next one was a T. Because this is a fundamentally random process. Now, we don't think it's a fundamentally random process. The way that stars behave, the way that ice gets laid down, the way that trees grow, the way that, well, anything happens. We don't think the world just does random stuff. But why? Because remember, the whole idea behind induction is that we don't know the general principles. We don't know the principles that actually govern the things we observe. So we're trying to figure them out. We're making the observations. We're looking for the patterns in the data we found about the observed cases in order to figure out those general principles. But remember that what those general principles are doing, I mean, the general principles of science are the laws of nature. They're the things that tell us how stuff works. So before we find them, we don't know how it works, right? Like, before people figured out the law of gravity, no one really understood why things fell the way they did. We just knew, like, oh, stuff falls. Right? Before people figured out the way gravity works, you had smart people like Aristotle saying, well, stuff falls here, right? If it's nearby me, it falls. But it looks like up there in the night sky, stuff ain't falling. So, people like Aristotle concluded, there were different gravitational rules for different parts of the universe. Right? The laws in one part of the universe worked one way, and the laws in another part of the universe worked another way. And so, given that we don't know the laws of nature and we're trying to figure them out when we do science by induction, well, doesn't that mean we don't know that we're not in this kind of situation? The kind of situation we have with the flipping of the coin? I mean, it's a fundamentally random process. How do we know that nature isn't fundamentally a random process? You might say, well, because we can see it's not random. We can see the regularities. But what you're pointing out there is there's a pattern in the observed cases. But the unobserved cases, all the cases in E that aren't in O, are so much larger than the set of observed cases that it should raise the worry, what if our situation is we're like this person who's observed from 5 through 17, or, with whatever results you got, just whatever patterns you found. What if it's a fundamentally random process, but like all fundamentally random processes, it falls into patterns in the short term? What if there is no law of gravity? Right? What if there's nothing fundamentally making objects fall towards the Earth and keeping planets in their orbit? What if random stuff is happening and for a little while it's produced the world we observe? You might be like, a little while. It's been this way forever. But you don't know it's been that way forever. You know personally, like if you're taking Descartes' approach to it, that like you have to start with, what you feel, what you are directly aware of. All you know is it's worked while you've been alive, and really while you've been looking while you've been alive. Let's say you trust other people. Okay, well, through all of recorded human history, it's worked this way. And maybe you think, well, if gravity didn't work, like human beings couldn't live. So we know that like through all of human history and all animal history, through all life on Earth, right, it's worked. But we only have for life on Earth, right? So life on Earth is supposed to have started 4 billion years ago. Now, there's induction actually being used in coming up with that number, but put that aside for one moment. But we also think the universe is 13 billion years old, I think. So most of the universe happened before life on Earth. How do we know stuff just wasn't happening at random before life on Earth? How do we know there was gravity? Right? You might think, well, we know that the planets formed, like Earth is older than 4 billion years old. Okay, I mean, you're actually going to have to use induction to do that. And the whole idea here is there's something fishy about induction. But if you actually look at the observed data, if you actually look at the data that human beings have observed and recorded, it's such a small part of what we think time is, and it's in such a small region of what we think space is, that it seems like if the universe is fundamentally random, this could just be a weird fluctuation of the randomness that produces an apparent order, and it might fall apart any moment. Here's the point. The point is that in order for induction to be legitimate, in order for it to be legitimate to say that the pattern that holds true of the observed cases is also going to hold true of all the cases, of everything, it seems like you have to assume that the same laws, the same fundamental set of laws, are operating everywhere and at all times. This is called the uniformity of nature hypothesis. or let's call it thesis to make it seem fancier. What it basically says is the same laws operate in all places and all times. And really here you should be saying the same fundamental set of laws, because of course there's some laws that don't apply in some cases. So like if you have laws governing population genetics, well, that doesn't have anything to say about rocks, right? Rocks don't reproduce. But the idea that people like Hume had, that really everybody had during the scientific revolution, is special laws. Laws that only apply in some restricted area are true because there's more general laws that explain why they're true. And the thought most people had is, well, in the end, physics is going to discover the most general set of laws, the laws that govern how everything behaves. And the point Hume is making, the first point, this is only the first step of the argument, is that for induction to be a legitimate intellectual move, for inductive inferences to be valid, for it to make sense for you to accept the conclusion of an inductive argument, which is an argument that goes from a set of observed cases to drawing conclusions about all cases. In order for that to be a valid inference, you have to know that the uniformity of nature thesis is true. And then Hume's question is going to be, well, how do you know that? And his question takes on extra force when you add to it, how do you know that if empiricism is true? How do you know that if the only things we can know, we know by observation? And I'll pick up that part of the question when with the next video.